Hi Year 11, here's our third lesson for the topic of probability. In this lesson, we'll look at the laws of probability. So far we've gone over everything we learnt about probability in years 8, 9 and 10. Then we looked at set theory and Venn diagrams. There are two laws or rules of probability that we use. The first one is the addition law. And it says that the probability of A union B is equal to the probability of A plus the probability of B. Take away the probability of A intersection B. And we can see this easily from a Venn diagram. So suppose we have overlapping sets, A and B, and we want to find the probability of the union of those two sets. Now, if we add the probability of A plus the probability of B, we've added this overlap twice. So all we have to do is take one of them away. So that's the addition law. We also have the multiplication law, and this states that the probability of A intersection B is equal to the probability of A multiplied by the probability of B. Now, for us to use this law, the events have to be independent, and we'll talk about that a little bit later on. Here's an example. An 8-sided die is tossed. Let A be the event that an even number is thrown. Let B be the event that a number greater than 5 is thrown. So let's draw this up as a Venn diagram. So A is even numbers and B is numbers greater than 5. So the overlap is going to be the numbers 6 and 8. And then in here will be the other even numbers 2 and 4. And in here, the other number that is greater than 5 is 7. And outside those two circles, we're going to have the numbers 1, 3, and 5. Okay, so the probability of A intersection B is 2 out of 8. The probability of A union B is going to be the probability of A, which is 4 out of 8, plus the probability of B, which is 3 out of 8. Take away the probability of A intersection B. And that's going to give us 5 out of 8. And you can see if we just count them up, 1, 2, 3, 4, 5, that this is correct. Now recall that if two sets have no common elements, then they are mutually exclusive. There's no overlap. And so in this case, the addition law is simplified because the probability of A intersection B is 0. Here's an example. An 8-sided die is thrown. Find the probability that an even number or a 3 is thrown. Now we can see that these events are mutually exclusive because 3 is not an even number. So the probability of even or 3 is the same as the probability of the even number plus the probability of a 3, which is a half plus an eighth, which is 5/8. Multi-stage events occur one after the other, and one of the best ways to list the outcomes of multi-stage events is with a tree diagram. A tree diagram lists the various outcomes for different events. Let's draw a tree diagram for the tossing of 2 coins. We'll start with the first coin. So this is our first event or first stage, and the options are heads and tails. Now when we draw our second event, or the second coin as it is in this case, we have to draw heads and tails off each of these options. So we're drawing it twice. And there's our tree diagram. Now we can easily use the tree diagram to list the sample space. We have got heads and then heads, heads, then tails, tails, then heads, and finally tails and then tails. In that previous example, the probabilities were equally likely. It's 50-50 whether you toss heads or tails. But if the outcome probabilities are not equally likely, we can create a probability tree. In addition to drawing our 2 stages and labeling them, we can put probabilities on the arms. Now this particular example looks at 2 days and whether we're going to get snow or not. And the probability of snow is 90% and the probability of no snow is 10%. So you can see how I've written that here. 90% for snow, and here, 10% for no snow. Let's have a look at how we use our multiplication law with a probability tree. Find the probability that it will snow both days. So we look at our tree and we find where it says snow and then snow. You might even like to highlight that. Now here's the rule. When we are going across the tree, we multiply because we're saying the word and. We want snow on the first day and we want snow on the second day. And in probability, and means times. So the probability of snow and then snow is going to be 90% times 90%, which is 81%. And now the addition law. Find the probability that it will snow on only one of the days. So in other words, snow on the first day, but not on the second. Or no snow on the first day, and then snow on the second. Here's the rule. When we are going down the tree, we add, because we said the word or, and in probability, or means plus. So we want snow and then no snow, or no snow and then snow. So we're going to do 90% times 10% plus 10% times 90%, which is 18%. Now some multi-stage events have the same probabilities for each event, and some have differing probabilities. The one we just did had the same probabilities, 90% and 10%. This is often to do with whether the first item is replaced or not. Let's have a look at with replacement. Sam chooses 2 counters from a bag containing 3 blue and 4 white counters. Draw a probability tree for the situation where she replaces the first counter after she selects it. So here's our first event, drawing a blue counter or drawing a white counter. And the probabilities are going to be 3 out of 7 and 4 out of 7. Here's our second event. So we're drawing the second counter, but we have the same probabilities because whatever she's drawn here, she's put back into the bag. So we're going to have 3 out of 7 and 4 out of 7, and then same down here. Now let's have a look at without replacement. So same situation, drawing 2 counters from a bag containing 3 blue and 4 white, but now draw a probability tree for the situation where she does not replace the first counter after she selects it. And what we've got to do to work out these probabilities is have a look at what has happened before that. So in this case here, she's drawn a blue counter, which means that for this arm, there's only 2 blue counters left out of 6. But there's still 4 white counters left. However, there's only 6 altogether. And a quick check, these 2 should add to 1. Now don't just copy these 2 blindly down here because we have a different situation. In this case, she has drawn a white. So when we come to here, we have 3 blue left out of 6. But in this case here, we've already drawn a white, we've only got 3 white left out of 6. Quick check, these add to 1. Now let's answer some questions. Find the probability that she draws different colours. So in other words, we want blue and then white, or white and then blue. So probability of blue, then white, plus probability of white and then blue. And remember, as we're going across the tree, we multiply, and then as we go down the tree, we add. So putting our probabilities in and into the calculator, we get 4/7. Find the probability that she draws at least 1 blue counter. Now, we could do this. The probability of blue and blue, plus the probability of blue and white, plus the probability of white and blue. But anytime you see these words, at least or at most, consider that you could work out the complementary event. So we could do 1, that's the total of all the probabilities, take away the thing we don't want, which is white, white. And that's a lot easier to work out. So 1 take away 4/7 times 3/6, which is 5/7. And finally, independent events. 2 events are independent if the probability of A intersection B is equal to the probability of A multiplied by the probability of B. Now this will only happen with non-mutually exclusive events. And let's have a think about why that is. So do you remember what mutually exclusive events are? There is no overlap. We can represent them with disjoint sets. And the probability of A intersection B is 0. which means that this is equal to 0. So either the probability of A is equal to 0 or the probability of B is equal to 0. And this makes the whole thing nonsense. This means one of these cannot happen. It's impossible. So how can an event that is impossible be independent of another event? So, two events are independent only if they're non-mutually exclusive and if they follow that rule. Here's our final example. A die and a coin are tossed simultaneously. Let A be the event that heads is thrown. Let B be the event that a number greater than 4 is thrown. Determine if the events A and B are independent. Now I'm going to use the total sample space, which is heads 1, heads 2, all the way up to head 6, and then tails 1, tails 2, etc. 12 outcomes. The probability that we throw heads is a half. The probability that we throw a number greater than 4 is 4 out of 12, or 1/3. Now what's the probability of A intersection B? In other words, heads and a number greater than 4. That's heads 5 and heads 6, so 2 out of 12, or 1/6. Now let's multiply these probabilities together. Probability of A times the probability of B is 1/6. So because the probability of A intersection B is equal to the probability of A times the probability of B, the events A and B are independent. Okay, that's it. Our final lesson for this topic is on conditional probability.